So good afternoon, everyone, and welcome back to the fifth lecture on mechanical engineering design topic, that is material science or engineering materials and their applications. Whereas we will learn the different properties and structures of engineering materials. So the outline of today's lecture is introduction to engineering materials, and then structure and properties of engineering material. In the last, we will, if time permits, we will see the phase diagrams also. That too, if time permits. Otherwise, we will continue this tomorrow also in the next lecture. So, as far as materials are concerned, how do we generally define materials? Then moreover, engineering materials. Now, what is the difference between material and engineering material? Since there are n number of definitions in our regional languages, in the conventional way, and in the technical languages. So here I have briefly classified the definition of material according to different sources. Now, when we say according to Webster's dictionary, materials are defined as the substances of which something is composed or made of. Now, when we say material, the dictionary tells us substances of which something is composed or made of. Something is made from something. The next is engineering material. Now, this part is under consideration for us also. Now, when we say engineering material, now which is the material which are useful to engineer in the practice of his or her profession, used to produce products according to the need and demand of the society. Now here, the material, fundamentally when we say material, it is nothing but the substance. Now when we say substance, the substance is obviously composed of elements. The basic constituents are the elements. Now wood is a material. Plastic, it's a material. Steel, it's a material. So these are the substances composed of their basic structure or the basic elements, physical elements. Material science primarily concerned with the search for basic knowledge about internal structure. Now, since the word science is there, it means we have to study the internal molecular structure, properties and processing of material and their complex interaction of relationship. This is what is expected from a technocrat or an engineer. The next is material engineering. So please concentrate on these four different definitions. The third definition is material science. So material science is nothing but the internal structure, properties and processing. And the fourth one is material engineering. Now when we say material engineering, it is mainly concerned with the use of fundamental and applied knowledge of material, so that they may be converted into products as needed or desired by the society. Basically it bridges the material knowledge from basic science to engineering application. Now when we say material, let us consider wood. Now, what does material engineering is entrusted upon or is using upon? So that wood, we know that the wood floats on water. So this is the basic knowledge. This is the basic knowledge of this material. Now, when we want to use this basic knowledge in engineering application, then in that case we would be doing what we'll be doing is we'll be using this in making ships, in making yachts, and or similar applications. Wherein since we know that it will not sink. So this is material engineering. Material engineering. Now, when we are learning the basic of engineering material, first we should well be aware of the basic definitions of all these three different aspects. Engineering material, and what is engineering material science or material science, and material engineering. Material engineering. Engineering material and material engineering. So it is mainly concerned with the knowledge of material, and that knowledge is to be applied for various engineering applications or disciplines. The next, classification of materials. The engineering materials can broadly be classified as ferrous metals, non-ferrous metals. So non-ferrous, I have just simply written down aluminium, magnesium, copper, nickel, titanium. These are non-metals, or no, sorry, non-ferrous. Third or next type is plastics, thermoplastics oblique thermosets. Next is ceramics and diamond. Next is composite material. These are most widely used now. And the last one is a nanomaterial. I think the latest innovations, the latest research is going on using nanomaterials. We'll see one by one regarding the basics of these classification. The materials, the engineering materials are classified according to the nature or the properties. There is another way depending upon the applications. Now for engineering, any engineering application, we generally select a certain material based on its mechanical property, its physical property, chemical property, and the manufacturing property. The secondary point which is to be considered is the important aspect is cost. Cost is an important aspect. And the second most important aspect after these properties is the availability. Availability of the material is also an important factor apart from appearance, service life, and recyclability, because nowadays government is more emphasizing on this fact that the material which are being used in our day-to-day life should be recyclable. It should not have say a wrong or negative impact on our environment. That's why this particular aspect of cost and availability, out of which this availability factor is the promising factor for the industries, wherein generally these industrial setups are there where you get the availability of raw material. You just take the steel industries, where it is located. You just take the power station, thermal power stations, where it is located. So it basically points out the availability criteria, which is most important in deciding the location of these forms. The next one, these are the key aspects of material research. So please watch it carefully and try to get the basics of these materials. Now, when we say this is the generalized aspect of material used in day-to-day or engineering purpose. Yeah, because engineering is nothing but the application of, or say implementation of basic sciences in the day-to-day life using the engineering principles. So materials, metals, plastics, then textiles, then wood, then environmental. Again, this aspect I'll discuss later on. Now we'll go for metals. Again, metals are subclassified as ferrous and non-ferrous. So wrought iron, stainless steel, mild steel, these are ferrous products. Metals, non-ferrous When I say non-ferrous, copper, aluminium, brass, these are non-ferrous. Coming on to the plastics. So in plastics, we have got two distinct, I'll explain this also, thermosetting and thermoplastic. So polyester resin, melamine, we are using plates for this melamine. Then polyurethane. So these are thermosetting plastics. Now thermoplasts or thermoplastics, acrylic, polyethylene, polyvinyl chloride, PVC. We are using this product, say more profoundly. Even this acrylic is also used more profoundly in our day-to-day application or in our domestic purposes also. The next one is wood. Obviously non-metal, so it's nothing to be written about it. Wood. Then first is natural wood, pine, mahogany, oak. You might have heard this name mahogany. This mahogany, in Hindi it is mahogany. So this mahogany tree is very costly. Why? Because the surface finish and the luster it provides, natural luster, the cost of this mahogany, and as well as it is used in ships, furniture of the ships. It is lightweight, too costly, and the luster is ultimate. Natural luster is there. There is no need to even polish that. Oak trees are again. Then man-made plywood, chipboard, MDF. So this we are all using in our furnitures day to day. Even though the life is not so good, but the appearance is say quite appreciable. That's why we are using all this. Then again non-metal textiles, cotton, wool, silk. Then out of this man-made are dyes, fabric and threads. Now when we say materials, another material is now which is used for finishing, that is paint, varnish. So these are all different types or aspects of material research wherein we can put our efforts so as to get the right material for the right application at the right cost and availability. So this is all about the material itself. The next, this is just to represent what type of material we are having and how it is being used in the design and manufacture of the products. Now, when I say plastic, so you can very well see when it comes to plastic where it is used. Wood, composites, ceramic. You might have heard this name, ceramics. Then metals and fabric. So fabric is a more common element. I'm interested in composites, ceramics, and metals. Even plastics also. When we say plastic, so now as far as metals, again ferrous and non-ferrous. Some of the examples are steel, stainless steel, high-speed steel. Whereas stainless steels we are using in utensils, steel in structural work, high-speed steels in metal cutting operation on our machine tools, that is lathe machine, cast irons for different casting purposes, specifically the bases and the structural elements of machine tool, and numerous examples are there where these castings or these cast irons are being employed. Non-ferrous, aluminium, copper, brass, titanium. Now, here this is simply a comparison, or rather to be more precise, an information regarding how the alloying is done and how to get the desirable properties out of this alloying. So alloy of, basically mild steel alloy of, obviously carbon. Iron is there, again carbon iron is there, stainless steel, slight use of nickel and chromium because we have to give it a super surface finish or the polish or the luster at the surface. Cast iron, obviously carbon percentage would be increasing. Wrought iron is almost, it is also known as the basic iron or the ore iron, wrought iron. 100% iron is there. Ornaments are the main, say, product of this wrought iron material. Gates, then railings. So ornamental gates are, right now it is more and much preferred. Cast iron is casting, no problem. Non-ferrous, you get window frames, aircraft. It is aluminum is used in aircraft body. Yes, in most of the fabrication work, internal fabrication work. Copper, electric wiring, tubing, kettle, bowls, pipes, etc. Brass, parts of electrical fittings, obviously ornaments. Lead, solders, pipes, batteries. Yes, lead acid batteries are there. So roofing, it is also used in roofing also. Now the next is introduction to, say, plastics and thermoplastics. Now this is the part which we are much interested as far as engineering design is concerned, because these two elements are giving a promising result, and every single day we are getting an update regarding the innovations done in these two materials, that is plastics and ceramics. Now we'll discuss in the later stage also. So thermoplastic and thermoset and then elastomers. These are the three basic types, wherein I have simply mentioned here the names which are much familiar to us. When I say acrylic, sir, it is a thermoplast. Nylon, thermoplast. Polyethylene, thermoplast. Thermoset, epoxy resins. You might have heard this name, epoxy resins, where that product which is used as an adhesive, araldite, phenolics, polyesters. Elastomers, the best say product is rubber. So here it is given, silicons, polyurethanes. So these are the basic products of this. Ceramic compounds are both metallic and non-metallic elements. It includes oxide, alumina, insulation, abrasive, zirconia, dyes for metal extrusion and abrasives. I think the diagram itself is self-explanatory regarding the ceramics, carbides, tungsten and other. So these are the basic applications. Wherein we can say that so nitrides is again the best example. Yes, composites. A wide spectrum of composite materials is around us now. But what do we mean by composite and how it is manufactured? You might have heard GRP, glass reinforced plastic. It is a composite. It's not pure plastic. Yes. Nowadays, the panels are being manufactured from that composites. A composite is a combination of two or more chemically distinct materials whose characteristics are superior to its constituent acting independently. So this is how the things are. Aerospace industry, offshore structures, it is quite visible from the photographs shown in this PPT itself, that how it is being used. Boats, definitely, and the sporting goods. So composites are everywhere now. Best composites are those having very good mechanical or tensile strength and less or very low per low per unit weight. Low per unit weight. Very less unit weight is there. Ceramic matrix, metal matrix, and laminates. So this particular material is again very much useful. Now see why I am emphasizing on these facts, that the 1 mark question includes the basic ideas and applications also. So generally 1 mark question includes all the above slides, wherein we can say that the material, classification of material and its applications. We'll see in detail the different types. Now the nanomaterials, because since in our classification we have shown nano also, so it should be there. It should be there. Nanomaterials. Yes, this nanomaterial, and now it is a revolution basically in the material science, where that's why this is now being made as a separate branch of study in material engineering, nanotechnology, wherein the particle size is in nanos, yeah, in nanometers, 1 to 100 nanometer, less than, the particle size is less than, wherein now you please concentrate on this classification, that is how the nanomaterials are being classified, and the basic element is particle size. Yes, 3-dimension, 2-dimension, 1-dimension, reduction in size in different coordinates. And now see the example, quantum dots, nanoparticles, nanotubes are there, nanowires are there, nanofibers are there, thin films and coating. Now there will be an age wherein the transplantation, yes, the heart, even your dental transplantation, even the cavities are being well taken care of by these nanoparticles and nanotubes, nanofibers. So, and it is giving a promising result. So this is how the application. Silver nanoparticles have good antibacterial properties and are used in surgical instruments, refrigerators, air conditioners, water purifiers. Gold nanoparticles are used in catalytic synthesis of silicon nanowires, sensors carrying drugs, and in the detection of tumors. Now see how an engineering material is being utilized in medical sciences. As I have already mentioned, giving a very promising result in medical sciences in the treatment of liver, then intestinal problems and heart problems. Nanoparticle is being used. And nowadays, since the technology is advancing, so in the detection of tumors also. So piezoelectric devices and chemical sensors and ultraviolet light emitters, these are nothing but the basic applications of nanoparticle. There are lot many more. Now mechanical engineers have introduced in automobiles also this nanofluid. Yes, as a coolant in our IC engine setup. So now this nanoparticle is being utilized in automobiles also. Then the next, as I have mentioned, the alternate classification of material uses categories based on its properties. When I say structural material, the materials which are used for making or fabricating or manufacturing these structures. Now, what do you mean by structures? We all know structures are nothing but the assembly of different linkages which either takes up the load or transfers the load. Next is electronic material. Number 3 is a magnetic material. Number 4 is semiconductors. Optical materials or semiconductors. Now, since we were as we are interested, as far as our syllabus is concerned, we are much interested in the classification based on properties. Now based on categories, so I have just simply given here when it comes to structure or the type of bonding which we are using as for semiconductors, this is for semiconductors. So I have given simple properties, that is the intermediate conductivity is extremely sensitive. So this is all regarding semiconductors. Now the next and the most important is structure and properties of engineering material. This was the introduction to the engineering materials. So we have seen different types of materials used in engineering practices. Now coming over to the very basic structures. Now depending upon the structures we will use, we will apply, we will utilize the functional ability of that particular material or metal or non-metal depending upon this study. Now there are some basic definitions or terminologies which must be understood before going for the structural analysis of any engineering material. So the number one is, when we say solid, a material is in solid state. So how a material can be? So a material can be in solid state. Yes, it may be in amorphous state. Yes. Now when I say amorphous state, in the same way I can say it as crystalline and non-crystalline. So amorphous is also known as non-crystalline. And when I say crystalline, it means solid, which differs substantially in their properties. Obviously, it differs in their properties. So how far structure is important for us as a mechanical engineer? First of all, you please concentrate on crystal. What is a crystal? Then crystallography. We'll see, go one by one. Just take the example of your sugar crystal. Now, what do you mean by that? Sugar crystal, sir? It is a solid that possesses long range order. Obviously, if you look upon to this particular sugar particle, or that sugar element, so it seems from the top, okay, it's a small tiny particle, but it's a long range. As in crystalline solid, there is a regular pattern of arrangement of particles which repeats itself periodically over the entire crystal. So inside that small particle, sugar particle, there is a large family of well-defined structure. The arrangement of the atoms at one point in a crystal is identical, and that arrangement is identical also. Now when I say arrangement is identical, we must first go to these diagram and then we'll come back to this. Yeah, so this is, so it has a regular boundary, it has a regular arrangement there. When we say a cube or a cubic body or a cubic structure, it has a definite shape. Yes, these are the definite shapes which we will subsequently in the next slides we will definitely be going through. So these are the basic structures of crystals. So a small tiny crystal is defined as again the material or a solid material, okay, and having some regular pattern of arrangement of the particle. Next is crystallography. Now when I say crystallography, it describes the ways in which component atoms are arranged in crystal and how the long range is achieved. Just now we have seen there are long chains in the crystals, in the materials, in the solid materials. Then how that arrangement is done, the description of arrangement of these crystals, long range crystals, is known as crystallography. The study is known as crystallography. Many chemical and physical properties depends on crystal structure. When I say, and it is but natural, it depends on crystal structure. We will see how it is affecting. And the knowledge of crystallography is essential if the properties of material are to be understood and exploited. This we'll see later on. Space lattice. When we say space lattice, it means that the cubic arrangement So when I say cubic arrangement, it means that the arrangement of particle, or the bodies, the arrangement of particle or the bodies. Let us see this. Say, for example, so this is the body. Now, wherein we say that the arrangement of crystals, say this is 1, 2, say 3, and say 4. So say behind this is 5, 6, 7, and 8. Now these arrangements would be required for the framework. You have to define it. How to define the long chain? We cannot define the long chain. We have to define the unit cell out of that long chain, because a material is made from a very long chain. Now if you see, say for example, you let us take this example of pencil. If I cut this pencil from here, what you'll be getting is, sir, a lead of some diameters, say 1 mm, 2 mm diameter is there, and then nothing but the wood. If you cut the tree from its stem, what you'll be observing is a regular pattern of that particular tree or the stem. On the stem, again you cut, you'll see the same stem, you'll see the same pattern. Yes, you'll see the same pattern. You please concentrate how we can see the same pattern in this fashion. So this is the pattern in which the tree, if stem is cut. So now I can say that when or going through the space lattice, a space lattice provides the framework with reference to which a crystal structure can be described. So these are nothing but the framework. So frame point, space lattice, this point, space lattice 1, 2, 3, 4, 5, 6, 7, and 8. So these are known as space lattice. Now, a space lattice is defined as an infinite array of points in 3 dimensions, in which every point is surrounding identical to that of every other point in the array. An identical array is there, a long chain is there. Say this is block 1, again same block 2, again same block 3, same block 4, same, and the long chain of the material. This is called space lattice. So this is the space lattice. I'm repeatedly telling you, this is the space lattice. Now the next terminology is basis. In order to obtain crystal structure, see structure, if you concentrate on this box, which I am showing repeatedly, if you concentrate on this box, it is nothing but the structure of a crystal, for example. Then what is space lattice? These points are the space lattice. Now what do you mean by basis? In order to obtain crystal structure, an atom or group of atoms must be placed on each lattice points. Mind well. These are space lattice points wherein an atom must be placed over each lattice point in a regular fashion. Then this act as a building unit or a structural unit for complete crystal structure. So these are space lattice, and this space lattice, when placed with some atom or group of atoms on these lattices, then it forms crystal structure. That's it. So it forms crystal structure. The last definition, as far as lattices are concerned, unit cell. Again, there are some definitions. A unit cell is the smallest component of the space lattice. Thus, the unit cell is a basic structural unit or building block of a crystal structure by virtue of its geometry and atomic position within. So you go on placing 1, 2, 3, 4, 10, 100, 1,000. So it will form a body. A unit cell is the smallest entity. It is the smallest component of space lattice. So space lattice decides the framework. Basis is nothing but to put atoms or group of atoms on the space lattice, and a unit cell is nothing but the smallest component which constitutes the very basic geometry and helps in building as a building block for the total chain or the structure. Next, now this is what we were discussing from last two slides, the structure, and this is the latest parameter of a unit cell. So this is a unit cell. This is a unit cell wherein it is divided into ordinate system as x, y, and z, x, y, and z, wherein point P, Q, and R are the edge lengths at all these three axes. The unit cell is formed by primitives. Primitives means smallest part, or intercepts A, B, C along x, y, and z. So A, B, and C are the intercepts or the distances marked on x, y, and z axis respectively. Alpha, beta, and gamma are called interfacial angles. These are nothing but interfacial angles. Yes, when I say alpha, it is interfacial angle between z and y. Beta, it is between x and z. Gamma, it is between x and y. Obviously, if the values of these intercepts and interfacial angles are known, one can easily determine the form and actual size of the unit cell. So the primary task is to define the lattice, crystal lattice, unit cell, which we have already done, because in the crystallography we have to learn all these things. Next thing, primitive cell. Again, primitive cell is the smallest geometrical shape. This may be defined as a geometrical shape which, when repeated indefinitely in 3 dimensions, will fill all the space and is equivalent of one lattice point. So that one single lattice point on this structure, say if this is lattice structure, this one single point, when again subdivided, is known as primitive cell. In some cases, the unit cell may coincide with the primitive cell, but in general, the primitive unit cell differs from the latter in that it is not restricted to being the equivalent of the lattice point. This is again a very say simple aspect, because in most of the applications, the geometry which is well defined, as a lattice point may not be the restriction for all the cases. The unit cell may be primitive cell, but all the primitive cells need not to be unit cells. This is again the same thing which is being repeated in the above 2 or 3 lines which I have detailed now. Next is types of crystals. Most crystalline solids are made of millions of tiny single crystals. Now see, please concentrate on this diagram. This is how the crystals are connected in a chain. And this microstructure is also known as polycrystalline. These grains are oriented randomly with respect to each other. Now these grains or these particular polycrystalline solids are made from tiny single crystals or grains. So again, this is the important aspect as far as crystallography is concerned. Now, the next is single crystal and polycrystalline crystal. Any single crystal, however, no matter how large is a single grain, single crystal of metal, many cubic centimeters in volume, are relatively easy to prepare in laboratory. Obviously, the crystals are being generally prepared now. Single crystal represents a material in its ideal condition and are produced artificially from their vapor or liquid state. Example, sugar. Yes, sugar, single crystal. Sodium chloride, common salt, diamonds. These are known as single crystals. Now, when I say polycrystalline crystals, it is an aggregate of many crystals usually known as polycrystallines separated by well-defined boundaries called as grain boundaries. Now here the thing is, when I say well-defined boundaries, it means every crystal has its unique identity. And obviously, due to number of aggregation of many crystals, so the strength is very high. Most of the materials, since we are using the composites now, so most of the materials have different orientations. We'll see what do you mean by orientations. Then these crystals are also called isotropic. Generally, they exhibit the properties same in every plane and direction, whereas single crystal is called anisotropic because it is single. No? It is single, and here it is in every single say crystal is attached with another crystal. So the polycrystalline. Again, the next definition, atomic radius. When I say atomic radius, this is defined as the half the distance between nearest neighbors in the crystal structure. In the crystal structure. So if this is the crystal structure, then what is the radius? The half the distance, half the distance. Say this is half the distance. This is called radius. Half the distance between the nearest neighbor, in the crystal structure of a pure atomic radius is denoted by R and expressed in terms of cube edge element A. So I'm repeatedly showing you this cube edge. Now another important aspect is atomic packing factor. This is defined as the ratio of total volume of atoms in a unit cell to the total volume of unit itself. Yes, this is also relatively generally called as relative density of packing. Yes, how compact it is, how much total volume in a unit cell to the total volume of the unit cell. Yes, total volume, how much volume is there in the structure known as atomic packing factor. So number of atoms multiplied by volume of one atom divided by volume of unit cell. So this is atomic packing factor, or rather more precisely relative density of packing factor or density factor. The next element is the density of crystal. Generally, what is density? We used to use this particular terminology in the design, that is mass upon volume. Obviously, mass upon volume of a material of a certain crystal now. So density is again here the same thing, mass of unit cell upon volume of unit cell. Now, when we say mass of unit cell, it is nothing but atomic mass upon Avogadro number into number of atoms per unit cell. So this is mass of unit cell, where M number of atoms per unit, Na Avogadro number, and M the atomic weight, and A the side of cubic unit, this side which we have discussed regarding atomic radius. Now the next element is, we are coming very close to the structural property, and then we'll go for the phase or the phase diagram, because after phase diagram we can very well discuss the iron carbon diagram and then the say stress and strain diagrams of the materials, different materials, and how does it affects. When I say direction, lattice plane and Miller indices, out of this direction and lattice plane, Miller indices are the most important point in deciding the crystalline or the structural aspects of any material. In a crystal, there exists direction and lattice plane which contains a large concentration of atoms. Various properties of crystals, particularly mechanical, are connected with the structure of crystal, though with the help of crystal direction. Now, when we say mechanical property, it means between two atoms there is a mechanical bond. Generally, these bonds are classified as covalent bond, ionic bond. But in mechanical, we generally used to call these bonds as van der Waal bonds. The metallic bonds are generally known as van der Waal bonds. Now, we'll discuss this later on also. Crystal direction, to specify the direction of a straight line joining lattice point in any crystal lattice. We choose any lattice point on the line as the origin, and the vector joining this to any other lattice point on the line decides the crystal direction. Yes, that is called crystal direction. Next, crystallographic plane. So these planes are crystallographic. These planes are crystallographic. The crystal lattice will be regarded as made up of an aggregate of set of parallel equidistant plane passing through this lattice point, which are known as lattice planes or atomic planes. So these are nothing but the same planes which passes through the point. So the next element, Miller indices. Miller indices of a direction are simple vectors or vector components of the direction resolved along each of the coordinates. Expressed as the multiples of unit cell parameter and reduced to their simplest form, they are denoted by H, K, and L. As we have already seen, Miller indices of the plane is a method to designate a set of parallel planes in a crystal by three numbers H, K, and L. You might have observed this thing. Yes. These are the three mutually perpendicular planes. So this is XY plane, this is XZ plane, and this is YZ plane. So based on this, we can say that these are nothing but the Miller indices, wherein we can designate parallel planes in a crystal by three numbers H, K, and L. Interplanar spacing. Now, these are the distance between planes and are represented by a number of parts of body diagonals. Now, when I say body diagonals, so these are the between the two space lattice. This is body diagonals. Yes. So, in terms of Miller indices, the distance between planes can be calculated from cubic system A is equals to B is equals to C. Because in cubes, the length, the height, and the width are nothing but same, A, B, and C. So that's why the interplanar spacing can be well written as A upon. For cubic system, for triangular, or for other geometries also, we can have the formulas. Now, coordination number. The number of nearest, please mind well, the number of nearest atoms directly surrounding a given atoms, the value of coordination of 6, coordination number 6 is for simple cubic, 8 for body centered cubic, 12 for face centered cubic. So in close packed structure, this number is 12. Close packed. Again, we'll have to explain all this thing, because first the definition will be there, and then based on this definition we'll explain the geometry, and then we are going for that very soon now. So the coordination number of carbon is 4. The number of nearest neighbors of the carbon atom is 4. This low coordination results in relatively inefficient packing of the carbon atoms in the crystal. So carbon atoms with a low coordination, since the number is 4 itself. Now, the defects and imperfections in crystals. When we say defects, in ideal crystal, atoms were arranged in regular shape. So, say for example, when we say regular system, or the regular order 1, say 2, say 3, and 4, then in front of this again 1 dash, 2 dash, 3 dash, and 4 dash. In front of this 1 double dash, 2 double dash, 3 double dash, and 4 double dash. So a regular structure will be there. However, the structure of real crystal differs from that of ideal one. Real crystals always have certain defects and imperfection, And therefore, the arrangement of atoms in the volume of a crystal is far from being perfectly regular. Now, as far as the defects are concerned, we see the defects in mechanical engineering causing creep, causing the failure of the mechanical component. You just take the example of our railways, rails. So in hot summer, we can say that the metal expands on heating. Now, how the defect is induced in the material, that is important. Now, in the hot sunny summer days, if the temperature is 47, 48 degrees centigrade, and these rails are at say 2:30 p.m. or 3 p.m., when we say the temperature is high, the metal will expand. The metal will expand. Now, as the temperature was 48 degree, all of a sudden, say rain comes or someone throws water over that rail, some portion of that rails, then what will happen? So obviously quenching effect will be there. Now, what do we mean by quenching effect? Now, when we say quenching effect would be there, in that case, the bonds between two crystal lattice, yes, between two crystal lattice, say there are these 2 points are there, and there is a bond. I'll call it as a covalent bond. And in that case, due to expansion, this bond has been stretched. And if it would have been brought to the normal temperature in a regular fashion, then these bonds will be again rejoined, and there would be no defect or imperfection in bonding. But what happens? All of a sudden, if you pour some water, in that case, these bonds won't connect to its earlier location. Rather in hurry, it will not say connect to the original bond, but it may connect in this fashion. So there occurs the imperfection, imperfections. So look at this. So this is the imperfection. So this imperfection is again a geometrical aspect, and these imperfection can be studied in detail in the forthcoming slides. Now see, this is the crystalline defects. Point imperfection. The point imperfection, which are lattice errors at isolated lattice points. See, vacancy. It's called Schottky defect also. A, okay. Say D, say C. B, interstitial. Now see, these are arranged in one order. Again, this Mr. B is lying there in between. So this is called interstitial defect. Point imperfections. These are point imperfections. Number C, vacancy is there. See, some vacancy is there. There is not at all, no point is there. So this causes a defect. Frankel defect is also there. That is vacancy. Interstitial is there. Interstitial imperfection. And that interstitial imperfection is nothing but D. Here it is. So adjoining elements, say points, it is missing there. Vacant sites are also there. So this is called this interstitial, and the point where it is vacant, it is called vacant sites. So these defects will try to reduce the mechanical strength of the structure or the element. Now please see, I was talking about line imperfection. A linear disturbance, one-dimensional imperfection in geometrical sense of atomic arrangement, which can very easily occur on the slip plane through crystal, is known as a dislocation. So edge dislocation, screw dislocation and climb dislocation. When I say edge dislocation, this edge to edge dislocation would be there. When I say screw dislocation, please mind well, screw dislocation, the other side, it should have been in this fashion, in the, say, one thing is this one. So this is edge dislocation. The edge is dislocated from this point to this point. Some edge is dislocated. So that is edge dislocation, because that edge should lie at the same point of, at the same center. Screw dislocation. Now see, screw dislocation would be this, in this fashion. So climb dislocation, one element or one bond will climb over other in this fashion. So again creating the line imperfection. So surface and grain boundary imperfection, obviously when it is edge, it is surface. When it is surface, it is volume imperfections. Now these are the arrangements. Simple cubic cell arrangement. In this arrangement, atoms are present at each corner of the cell and their center coincides with each other. See, please concentrate. These are the simple cubic cell. Now rest of the part is quite clear, because 1/8 part of this atom is present in the cell, obviously, because it is attached with other 8 elements also. So that's why it is 1/8. This one at this one point, 8 different cells or simple cells are attached. Next, body centered cubic. Here this is called BCC. It is present at the center of the crystal, and each corner of the center of an atom is attached to this. This is called BCC. When I say FCC, face centered cubic, this body centered cubic, this point is there exactly at the center of all the faces, means in the box, in the cube. But this face centered cubic, the concentration is made at this center of the face itself, face centered cubic. In this arrangement, each face has an atom. So on each face, 1, 2, 3, 4, 5, 6. On 6 faces, you'll have that concentration. An atom is concentrated. Say for BCC at the mid of this, say, space lattice. Then for FCC, the atom is present at the center of each face of the structure. So this is called face centered cubic or crystal. I think this has some relevancy has been made for the structure of a body, because we have studied properties and now the structures. The next target is phase. When we say phase, a phase is a physically distinct, chemically homogeneous and mechanically separable region in a system in equilibrium. When I say a system, it means both mechanical and chemical homogeneity. And obviously it's a physical stage. So for defining the phase of a material, Gibbs phase rule is most widely used, and it is predominant and gives a very exact definition of this particular properties or phase of an element. When I say F plus P is equals to C plus 2, where F is number of degrees of freedom of that particular element, P number of phases present, C number of components in the phase. So based on this basic definition, definitely we'll be continuing the same tomorrow also, because after this we'll have the iron, carbon and the different structures shown. So it is related, phase equilibrium, when I say defined, it is related to consistency in physical and chemical characteristics of a phase with respect to time. So this is again now the phase diagram. It is basically temperature. Composition, space showing the stability of various phases. A phase diagram is also called as an equilibrium or constitutional diagram. or the constitutional diagram. Constitutional diagram, wherein it shows the relationship between temperature, composition, and quantities of phases. Now, what do you mean by phase? We'll try to understand this. We'll directly switch over to this diagram itself. Now, please concentrate. Then again, we'll go back to the slide. So this is the phase which I was talking about. Just look at this. This is simple nickel copper as a sake of understanding. So composition is how far we are. So this region, this is phase diagram. But in this portion is nothing but solid. This is liquid plus solid. So liquidous but contains solid also. This is stage. And the last one, obviously, temperature has to do with this. Temperature has to do with this. So this is the phase diagram. This is the phase diagram which is to be represented, obviously by this. So again, types of phase diagram: single component and multi or two component. So generally it is used for carbon and pure metals, single component. And since the carbon and pure metals, they are nowadays not in very common use, because we are much going for the compositions, two or more than two elements. So, but still, the examples of the single components such as water, graphite, metallic carbon, diamond, etc. Now, binary phase diagrams are most widely used. Often, the material which are completely soluble in liquid as well as solid state, binary isomorphous system. Since the most metals are completely soluble in solid state, the only type of solid phase form will be substitutional solid. The two metals will generally have the same type of crystal structure and differ in atomic radii by 8%. As we have seen, the atomic and the radius also. So CuNi is one of the example of these types of phase diagram, mixes with each other, copper and nickel. And now the same thing I have shown. So this is the basic structure of this phase diagram, wherein in between the solidus and liquidus line, there exists two phase region basically. Two phase regions. It is a mixture of both solid and liquid. So this is Mischy type. You must say that the both the state will be there. Now, as far as this upper portion is concerned, again liquidus, and this is solidus. So these are nothing but the basic phase diagram for the metal. So the topic will be continued tomorrow, along with the in-depth details of stress strain curve and again the properties defined for the material. Thank you. Thank you so much for today's lecture. Thank you. Thank you, madam.